So for section 8.4, we're going to talk about slope fields. So we've been looking at first order differential equations in this particular chapter or unit. So for example, we've been looking at dy dx is equal to x squared. So again, we both have, when you talk about a slope field, we can look at these derivatives as a formula that produces a unique output of what values of x and y are given the inputs. So for example, at the point 1, 2, we can plug in 1 for x and 2 for y and get an output. So if we interpret y prime as the slope of a tangent line, then the differential equation states that at each point x, y on a curve, the slope of the tangent line equals the value of f at that point. So we can now give a geometric description to our differential equations. So when we take a look at the slope field, a slope field is the graph of what the differential equation is going to look like. So it's a geometric description of the set of integral curves that can be attained by drawing small line, which are the slopes of the tangent line through those points. The resulting picture is called a slope field, or a direction field for the differential equation because it shows the slope or the direction of the curves at each point. The more slopes that are shown, the more accurate the curve is going to be. So for example, this is what an example of what a slope field is going to look like. As you can see in these two diagrams, notice we've just got small tangent lines drawn at each particular. So at 1, 0, here is the slope of a tangent line. Now obviously, as you can see, when they say the more points that are represented, the more accurate the field is going to be. So the first thing when you're constructing a slope field that you have to do is we're going to have to identify and approximate what the slope of the tangent line is going to be at each particular point. So you can do this by building a table of values. So for example, here is a derivative, y minus x. So to calculate what the slope of the tangent line is going to be at a particular point, for the example when x is -3, y is -3, I'm going to plug in -3 for x and -3 for y. So -3 minus -3 is going to be -3 plus 3, which is just 0. Plug in -3 for x and -2 for y, so I end up with -2 minus a -3, which is going to give me a 1. So then -1 minus -3 is going to give me a 2. So what I can do then is draw small little tangent lines at each of these points to construct the slope field. So then x is -2, y is -3. -3 minus a -2 would give me a -1. -3 minus a -1 would give me a -2. So now the way you actually sketch these small little tangent lines, for example with a slope of 1 or slope of 2, here's kind of a safe rule of thumb. When you're constructing a slope field, if you end up with a slope of 1, you should make about a 45-degree angle of that small tangent line to the horizontal. So for example, there's a good estimate for a slope of 1. Again, we know horizontal lines have a slope of 0. So obviously, the smaller your slope, the smaller and smaller, they're getting closer and closer to 0. They're getting more and more horizontal. Now, if you've got an undefined slope, we know that it is going to be a vertical line. So the larger your slope, the closer and closer to being vertical that line is going to be. So that's how you show in demonstration when you're building your slope field. So for example, let's draw slopes for the following slope values. So for example, if I want to sketch a line, a small tangent line with a slope of 1, again, I'm going to draw about a 45-degree angle with a horizontal. I know 2 is greater than 1, so that's going to have to become more and more vertical. So I would show that a slope of 2 is a little bit steeper than a slope of 1. A slope of 3 is going to be even more steeper than a slope of 2. 4, I know, is even going to be steeper. 10 is going to be really steep. So that, as you can see, notice as the value of my slopes are increasing, my slopes are becoming more and more vertical. So now let's take a look at these slopes, a slope of 1/2. So I want to make that flatter than a slope of 1. 1/3 I know is closer to the 0 than 1/2. So I want to flatten that out. 1/4, and then 1/10 is really, really close to 0. So you want to show that horizontal. So you want to show how these particular slopes are getting flatter and flatter, closer and closer to being horizontal. You can use the same idea for -1 on the negative side. So -1, again, I'm going to draw about a 45-degree angle with the horizontal, but I want to make sure that it is decreasing and has the negative slope. Again, now -2 is getting further away from 0. So this is actually going to be steeper. -3, -4, and -10. Now notice in these negatives, here's my -1/2, these values are getting closer and closer to 0. So more and more horizontal. This one should probably be a little bit more flatter. There we go. Now, when you have to sketch a slope of a tangent line that's equal to 0, I'm simply going to draw a horizontal line. Now, when you have to sketch a slope on a slope field that's undefined, you could draw a vertical line, or more commonly, you're going to see nothing at all at that particular point. They just don't draw anything. So, for example, let's go ahead and let's practice sketching some slope fields. So again, we want to sketch a slope field to represent the graph, the derivative 1/x minus 1. So what you want to do here on your slope field is imagine start where you have your x and y axis. So I'm just going to go ahead and put my x and y axis right here. So I'm going to start at 0, 0. If you want to, you can certainly build a little t-chart. So starting right here at the origin. When I plug in 0 for x and 0 for y, so 1/0 minus 1 is going to give me a slope of -1. So to show a slope at -1, again, I'm going to draw about a 45-degree angle for that particular slope. Now notice there are no y values in this particular derivative. So what's going to happen is you're going to end up having the same tangent line slopes vertically. Because notice if I plug in x is 0, y is 1, for example, well, when I plug 0 in again, I'm going to get another -1. So when you have a differential equation where you have just an x, what happens in your slope field is you're going to have the same slope vertically. So I then can just simply draw all my slopes of -1 anywhere that x is equal to 0. Now when x is equal to 1, I end up with 1/1 minus 1, which means it's undefined. So that means I don't have to write anything at 0. You could certainly write the vertical line segments, but you don't have to. When x is 2, 1/2 minus 1 is going to give me a slope of 1. So I'm going to draw that 45-degree angle, but now it's going to be positive. And again, they're all going to be the same vertically. So now when x is -1, 1/-1 minus 1 is going to be -1/2. So I want to make sure, compare it to my slope of -1. I want to make sure on my slope field I show that this is flatter than what I did it on the x equals 1. Or x equals 0. And then finally -2, that's going to give me a slope of -1/3. And again, you want to make sure these are more horizontal than the slopes you sketched for a slope of -1/2. So really you're comparing. So when you look at your slope field, you should be able to see that these slopes, this is a larger slope than these. These are getting smaller and smaller slopes. So now let's take a look at B. This is an example of a differential equation where you just have a y in it. So again, put your x and y axis somewhere on the grid. Starting with, again, notice there are no x's, you just have y values. So starting with a y value of 0, the slope will be 0. So anywhere where your y coordinate is equal to 0, you're going to have a 0 slope. So when you have a differential equation with just y's in your slope field, instead you're going to have the same slope horizontally. So So for x's, you end up having the same slope vertically. For a differential equation, which is just y, you'll have the same slope horizontally. So when you look at when y is equal to 1, you end up with a slope of 2. So I want to make this a little bit larger than a 45-degree angle. At 2, you're going to have a slope of 4. So you definitely want to show that it's steeper than a slope of 2. And then if you do -1, that's going to be -2. So since I already have a slope of 2 up here, what basically I want to do is make sure you show this close to steepness as you can, but on the negative. So when you see a slope field and you see that you have the same tangent line slopes going horizontally, you know the differential equation is going to be in terms of just y. When you look at a slope field and you notice that all the tangent lines have the same slope going vertically, you know the differential equation is going to be just in terms of x. Now it is possible that you have a differential equation with both an x and a y in it. So this is where it's helpful to build your little t-chart, because you're not going to have necessarily the same slope going vertically and horizontally. So starting at 0, 0, so 0 minus 0, I know at what origin my slope will be 0. So then I'll go to 1, 0. 1 minus 0 is 1. So that'll be my 45 degree. And then I've got 2, 0. So you make sure you show that that slope is steeper than what you sketched at 1, 0. And then I've got -1, 0. So -1 minus 0 is a -1. So a negative slope with a 45-degree angle. And then -2, 0. So -2 minus 0 is a -2. So here's 0, 0, here's 0, 1. So 0 minus 1 is going to give me a -1 slope. 0, 2 is going to give you a -2 slope. 0, -1 is going to give me a +1. 1, 1, 1 minus 1 is going to give me a 0 slope. 2, 1, 2 minus 1 will give me a 1. 2, 1, 2 minus 1 is going to give me a 1. 2, 2 will give me a 0 slope. 2, -1, 2 minus -1 will give me 3. Then we have -1, 1. So -1 minus 1 is a -2. -1, 2. -1 minus a -2 is going to give me a +1. -1, -1, -1 minus -1 will give me another slope of 0. And then we've got -2, -1. -2 minus -1 will give me a slope of -1. -2, 1. So -2 minus 1 is -3. And then -2, 2. -2 minus 2 is going to give me a slope of -4. And then I have the 1 at 1, -1. So 1 minus -1 will give me a 0. So you can see there is no pattern to this slope field in terms you don't have the same slopes going horizontally or vertically. That's when you look at a slope field, you know that you've got a differential equation that has both an x and a y. So sometimes what you have to do is they'll give you a slope field and they want you to sketch the graph that satisfies the initial condition. So for example, y of 0 is equal to 0. So what you want to do is assure that your graph passes through this initial condition 0, 0. So again, what you do is you kind of follow the pattern of the points here. So again, you're going to take this curve, and notice these slope fields are going to kind of curve down. They curve downward. At this particular point. So there's A. -1, 0. Again, I want to make sure that following these tangent lines, oh, wait a minute, 0. I want to, this is 0, -1. I'm doing C first. I apologize. There's C. And it kind of curves down. And now let me go back and do 0, 1. So 0, 1, you can see that the slope field passes this way. And then 0, 2. So now here's an example of them giving you the slope field and they're giving you the differential equation. So here is where we've got the slope field for the differential equation. Sketch the solution that passes through the point 0, 1 and 0, -1. So here's 0, 1. So again, what I want to do is assure me that this has a point that's passing through. So here's my 0, 1. So notice, follow these points. It's passing through. It looks like it's just going straight up. So there's 0, 1. 0, -1. Again, notice how the pattern of the curves, it's going to pass through this point and then curve back down.